Welcome to linear algebra. The whole subject is built on one object, and we are going to spend this first episode getting to know it completely. That object is the vector. Here's the first surprise. A vector is two things at once. It is an arrow with a length and a direction, the kind of thing you might draw to show a push or a journey. And it is also an ordered list of numbers, like the list 3, 4. These are not two different objects that happen to be related. They are the same object seen from two sides. The arrow is the geometric face, the list is the algebraic face. Almost everything we do in this course is translating between them. Today we will define how vectors add, how they scale, and how long they are. We will meet the spaces they live in, the plane, ordinary space, and spaces with more dimensions than we can picture. We will meet the zero vector, and we will see the two great interpretations, a vector as a physical displacement, and a vector as a row of data. Let's begin. Let's pin down both faces. Geometrically, a vector is an arrow, and an arrow carries exactly two pieces of information: how long it is, its magnitude, and which way it points, its direction. Notice what is not on that list, where the arrow starts. An arrow here and an identical arrow shifted over there, same length and same direction, represent the same vector. A vector is a displacement, not a place. Algebraically, a vector is an ordered list of numbers called its components. We write the list across in angle brackets or stacked up as a column. Both mean the same thing, and we will lean on the column form heavily once matrices arrive. Here is the dictionary that connects the two faces. Take the arrow and flight it so its tail sits at the origin. Then its tip lands at a specific point, and the coordinates of that point are exactly the components of the vector. The arrow is the list, drawn. The list is the arrow, measured. One last note on notation: we write components in angle brackets and points in ordinary parentheses. Same numbers, different meaning. A vector is a displacement. A point is a location. The first thing you can do with vectors is add them. Algebraically, this is as easy as it gets. You add componentwise. The first component of the sum is the sum of the first components. The second component of the sum is the sum of the second components, and so on. So the vector 3, 1, plus the vector 1, 2 is the vector 4, 3. Geometrically, addition is tip to tail, and this is the picture worth burning into memory. Draw the first arrow, U. Now pick up the second arrow, V, without rotating it, and set its tail down right at the tip of U. The sum, U plus V, is the new arrow that runs from the tail of U all the way to the tip of V. If instead you draw both arrows from a common starting point, the sum is the diagonal of the parallelogram they frame. That is why the order doesn't matter. U plus V equals V plus U, because the same diagonal closes the same parallelogram whichever side you walk first. Addition turns two journeys into the single journey that achieves the same net displacement. The second basic operation is scalar multiplication, multiplying a vector by a single number. In linear algebra, we call plane numbers scalars, precisely because their job is to scale vectors. Algebraically, you multiply every component by that number. So 2 times the vector 1, 2 is the vector 2, 4. Geometrically, multiplying by a scalar stretches the arrow. Multiplying by 2 makes it twice as long, pointing the same way. Multiplying by 1/2 makes it half as long. The sign controls direction. A positive scalar keeps the arrow pointing the same way, while a negative scalar flips it around to point in the exact opposite direction. So -1 times the vector 1, 2 is the vector -1, -2, same length, opposite heading. And multiplying by 0 collapses any vector down to the zero vector. Here is a definition we'll use constantly. Two vectors are called parallel when one is a scalar multiple of the other. They lie along the same line through the origin even if they have different lengths or point in opposite directions. How long is a vector? Its length is called the magnitude, and we write it with vertical bars on either side, like the absolute value of a number. To find it, square every component, add up the squares, and take the square root. In the plane, this is nothing but the Pythagorean theorem. A vector with components 3 and 4 is the hypotenuse of a right triangle with legs 3 and 4, so its length is the square root of 9 plus 16, which is the square root of 25, which is 5. The same formula works in any dimension, just keep adding square components under the root. The vector 1, 2, 2 in space has length the square root of 1 plus 4 plus 4, which is 3. Now, a special case we'll need everywhere. A vector whose length is exactly 1 is called a unit vector. To turn any non-zero vector into a unit vector pointing the same way, you divide it by its own magnitude. We call that normalizing, and we put a little hat on the result. A unit vector strips away the length and keeps only the pure direction. Where do vectors live? In the plane, every vector is a pair of numbers, and we call the plane R2, R for the real numbers, 2 for the two components. In ordinary space, every vector is a triple of numbers, and we call that space R3. The pattern is the engine of the whole subject. For any whole number n, Rn is the space of vectors with n components, one for each dimension. A useful set of landmarks in every such space is the standard basis vectors. In R3, these are the vectors 1, 0, 0, 0, 1, 0, and 0, and 0, 1, pure unit steps along the x, y, and z axes. Every other vector is built from them. The vector ABC is just A times the first, plus B times the second, plus C times the third. Now here is the conceptual leap that makes linear algebra so powerful. We can picture R2 and R3, but past 3 dimensions our eyes give out. That's fine. The arithmetic, adding components, scaling them, taking square roots for length, works exactly the same in R4, R100, R1,000,000. We stop drawing and start trusting the algebra, and the algebra never lies. Before we meet the zero vector, let's note that addition and scalar multiplication don't just work. They work nicely, obeying all the laws you'd hope for. Addition is commutative, u plus v equals v plus u. It's associative, grouping doesn't matter when you add 3 vectors. The zero vector is the additive identity, and every vector v has a negative v, that adds back to 0. Scalar multiplication distributes in 2 ways. A scalar times a sum of vectors spreads across the sum, and a sum of scalars times one vector spreads 2. And the operations are compatible. Multiplying by a, then by b, is the same as multiplying by a times b, and multiplying by 1 leaves a vector unchanged. There are 8 such rules in total, and here's the deep part. Any collection of objects with an addition and a scaling that satisfy these 8 rules is called a vector space. Rn is the prototype, but the same rules are obeyed by spaces of functions, of polynomials, of matrices. Once you know the rules, the word vector stretches far beyond arrows, and that generality is where this course is ultimately headed. Every number system needs a 0, and vectors are no exception. The zero vector is the vector whose every component is 0. Its magnitude is 0. It is the only vector with no length at all. It plays the role that the number 0 plays in ordinary addition. Add the 0 vector to any vector and you get that same vector back unchanged. We call it the additive identity. The 0 vector is a little strange, because unlike every other vector, it has no direction. Which way does an arrow of length 0 point? The question has no answer, and that's exactly why you cannot normalize it. Dividing by its magnitude would mean dividing by 0. Each space Rn has its very own 0 vector, sitting at the origin. It may look like the most boring object in the course, but it anchors everything. It's the origin we measure from. The center of every space will build, and physically it's the answer when a tug-of-war ends in a perfect draw and all the forces cancel. Let's see both operations on one canvas. On the left, 2 arrows leave the origin, u pointing right and slightly up, and v pointing up and slightly right. To add them tip to tail, we make a faint copy of v and slide it so its tail rests on the tip of u. The bold arrow from the origin straight to the tip of that copy is the sum u plus v. Notice the shaded parallelogram, u and v frame it, and the sum is precisely its diagonal. Walk along u then v, or along v then u. Either way, you land at the same corner. That's the parallelogram law made visible. On the right, scalar multiplication. Start with an arrow doubling it. 2 times w gives an arrow twice as long pointing the same way. Negating it, negative w, gives an arrow of the same length flipped to point the opposite way. All 3 lie on one straight line through the origin. That line is every scalar multiple of w, which is a preview of next episode's big idea. Here is the same idea climbing through dimensions. On the left, the plane, R2, one arrow, runs from the origin to the point 3, 4, and beneath it, a right triangle with legs 3 and 4 shows why its length is 5. Pure Pythagoras. In the middle, space are 3 axes drawn in perspective, and an arrow reaching to the point 1, 2, 2 with length 3. So far, we can see everything. On the right, Rn, there is nothing to draw, so we draw the only honest thing. A tall column of components, v1, v2, on down to vn, with the caption no picture, only arithmetic. That panel is the whole philosophy of the course in one image. When the geometry runs out, the algebra carries on, and it is just as rigorous and just as true. We trade pictures for formulas, and we lose nothing but our ability to look. Let's run the operations together. Take u equal to the vector 1, 2, 2, and v equal to the vector 3, 0, negative 4. We want 2u minus v and then its length. First scale, 2u multiplies each component of u by 2, giving the vector 2, 4, 4. Now subtract v component-wise. Subtracting is just adding negative v, so we do 2 minus 3, 4 minus 0, and 4 minus negative 4. That last one is 4 plus 4. The result is the vector negative 1, 4, 8. Now its length, square each component, 1, 16, 64, add to get 81, and the square root of 81 is 9. Clean. Here's a warning worth stating out loud. The length of u is 3, and the length of v is 5. But the length of 2u minus v is 9, not 2 times 3 minus 5, which would be 1. Length does not pass through addition and subtraction. You must combine the vectors first and measure the result. Never measure the pieces and combine the lengths. Now let's normalize a vector, turn it into a unit vector. Take v equal to the vector 2, -1, 2, and find the unit vector pointing the same way. Step 1 is to measure its length. Square the components, 2 squared is 4, -1 squared is 1, 2 squared is 4. They add to 9, and the square root of 9 is 3. So the magnitude of v is 3. Step 2, divide the vector by its length, which means dividing each component by 3. We get the vector 2/3, -1/3 2/3. That's our unit vector, and we mark it with a hat. Always sanity check. Square the new components, 4/9, 1/9, 4/9. They add to 9/9, which is 1, and the square root of 1 is 1. The length is exactly 1, as required. We've kept the direction of v intact and scaled its length down to a clean one. Normalizing like this is something you'll do constantly, whenever you care about which way a vector points but not how long it is. Let's end the examples with the interpretation that makes vectors run the modern world. Forget arrows and space for a moment. Picture a house described by 4 numbers, its square footage, 1450, its bedrooms, 3, its bathrooms, 2, and the year it was built, 1998. Stack those 4 numbers and you have a vector in R4. It points nowhere in physical space. Its 4 directions are features, not axes you can walk along. Now take a second house, 1600 square feet, 3 beds, 2 baths, built 2005. Subtract the first from the second, exactly as we subtract any vectors, component-wise, and you get the vector 150,007. That difference vector says the second house is 150 square feet bigger, identical in beds and baths, and 7 years newer. The arithmetic is identical to arrows, but now it's comparing houses. This is the data vector, and adding, scaling, and measuring distance between such vectors is the engine inside every recommender, every search engine, every machine learning model. Where did this idea come from? It's younger than you might think. Around 1800, Wessel and Argand pictured complex numbers as arrows in the plane, the first real hint that geometry and algebra could be the same thing. In 1843, William Rowan Hamilton invented quaternions, a 4-dimensional number system built to handle rotations in 3 dimensions, and it was Hamilton who coined the very word vector. The next year, 1844, Hermann Grassmann published a dense, visionary book that defined vectors and linear combinations, in any number of dimensions. Decades before anyone was ready for it, he was so far ahead that his work was largely ignored in his lifetime. In the 1880s, Josiah Willard Gibbs at Yale and Oliver Heaviside in England stripped Hamilton's quaternions down to the clean, 3-dimensional vector notation we still teach. And in 1888, Giuseppe Peano wrote down the modern axioms of a vector space, the abstract rules that let Rn, function spaces, and data spaces all be one subject. Let's recap. A vector is 2 things at once, an arrow with a magnitude and a direction, and an ordered list of numbers called its components. You add vectors component-wise, which geometrically is the tip-to-tail rule, or equivalently the diagonal of a parallelogram. You scale a vector by multiplying every component by a number, stretching the arrow and flipping it when the number is negative. The magnitude, the length, is the square root of the sum of the squared components, which is just Pythagoras. Divide a vector by its own length and you get a unit vector, pure direction with length 1. Vectors live in the plane R2 in space R3, and in Rn for any n. When we can't draw them, the arithmetic carries us through unchanged. The zero vector, all zeros, is the additive identity and the only vector with no direction. And a vector can mean a displacement in physical space or a row of data in a feature space. Next episode, we let ourselves scale and add vectors freely and ask what every possible result looks like. That collection is called the span, and it's where the real story of linear algebra begins. Today, we built the vector from scratch. A vector has 2 faces. Geometrically, it is an arrow with a length and a direction. Algebraically, it is an ordered list of numbers written in angle brackets or stacked as a column. Switching between the 2 pictures on demand is most of what linear algebra feels like. We add vectors component-wise, and geometrically, that addition is tip to tail. Place the tail of the second arrow at the tip of the first, and the sum runs from the first tail to the second tip. We scale a vector by multiplying every component by a number, which stretches the arrow and flips it around when the number is negative. The magnitude of a vector, written with vertical bars, is the square root of the sum of its squared components. Pythagoras applied to an arrow. Vectors live in the plane called R2 in space called R3 and in Rn for any dimension n, even when we can no longer draw them. The zero vector, all components 0, is the one with no length and no direction. And a vector can mean 2 very different things, a displacement in physical space or a row of data, a customer, a pixel, a word in some high-dimensional feature space. Next episode, we scale and add vectors freely and ask what the whole collection of results looks like. That is the span, and it is where linear algebra truly begins. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.